before talking about what the inverse of a matrix is, we need to talk about what the one is for matrices. What do I mean by that? Right, when we deal with real numbers, right? If we have a, which is a real number, then the number one, it's the number that does not change the result if you multiply that by a. So if you multiply, let me rephrase that. So if you multiply a by 1, it's not gonna change a. It's gonna keep a as a. If you multiply to the left or to the right, no matter what you do, a times 1 or 1 times a will actually be equal to a. Also, when a is not equal to 0, then if you multiply a by its reciprocal, right, a to the minus 1, which is 1 over a for real numbers, that's the same as the reciprocal times a, and it gives you 1. Okay, so maybe for an example here, if I do 3 times 1, that's the same as 1 times 3, and that gives us 3. And if I do 3 times 1/3, that's the same as 1/3 times 3, and that gives us 1. So we're trying to find what this one is. We call it, because of this equation here, the neutral element of multiplication. It's the element that does not change multiplication. So we're trying to find the neutral element of matrix multiplication. So what is the neutral element of matrix multiplication? Okay, well, let's try. To find it, I'm going to try to replicate this thing here. Okay, I'm going to choose, instead of a number a, I'm going to choose a linear transformation with standard matrix A. Example, so let A be the standard matrix of a linear transformation that we're going to rotate 90 degrees clockwise. That rotates 90 degrees clockwise. So A here, if you rotate I 90 degrees clockwise, you get minus j. You rotate j, you get I. Here we go, that's A. So this transformation, right, it takes the vector x, and then you rotate, right? So you do let's call this transformation TA. Okay, you're gonna get ax. Okay. Now we're trying to find the inverse of that transformation or that function, right? So we're trying to go from here to there. So we're trying to go back to where we were. So imagine we've got, like, a point. We've rotated 90 degrees clockwise. We're trying to go back to where we were. So what would take us back to where we were? Well, okay, let's call that transformation T A inverse. Okay, A inverse is going to be actually let's call it B. Okay, but eventually B is going to be A inverse. So B is the standard matrix that performs the transformation that takes us back to where we were, right? So here we rotate 90 degrees clockwise. Well, here, to go back, right, I'm pretty sure you figured out that we need to rotate 90 degrees counterclockwise. Okay, so the inverse of A is the linear transformation that rotates 90 degrees counterclockwise. Okay, so that's B. Let's call that B. So to rotate counterclockwise, I gets sent onto J. And if you rotate J, you get sent onto minus I. So that's that should be the inverse of A in some way, okay? So if this is the inverse of A, it means that A times B, so I'm going to do A times B. So A times B, so, right, I'm sort of doing this here. It should give me the matrix 1 that I'm looking for, okay? So A times B will be what? Let's calculate. Let's recopy. A is 0, 1, minus 1, 0. B is 0, minus 1, 1, 0. We multiply, we get 1, 0, 0, 1. So this should be our matrix 1, okay? We're going to call it also actually the identity matrix. And let's think about what the standard matrix does, okay? Let's look at this column. It's a linear transformation that basically sends I onto what? 1, 0. Oh, sends I onto I. This column here, that's where J gets sent. J gets sent onto J. So I stays where it is, J stays where it is. Actually, all vectors stay where they are when you apply the linear transformation with standard matrix I to a vector. So the linear transformation with standard matrix I is the linear transformation that does nothing. It keeps things where they are. So 1, 0, 0, 1 is called the 2 by 2 identity matrix. Okay. It sends, well, it's linear transformation, sends I onto I, J onto J, X onto X. Okay. It keeps points or vectors where they are. So if you multiply, okay, let's verify this. If I've got Ti, okay, let's say the linear transformation with matrix I. If I apply this, let's say x is x1, x2. If I apply I to x1, x2, notice we're going to get x1, x2. Things stay where they are. So in general, we've got I2, which is this matrix here. We've got I3, which is the identity matrix with, that's 3 by 3. So what's that matrix? It's the linear transformation, okay, that will take vectors in, right? It's gonna take vectors in R3, okay, map them into R3, but keep things where they are. So I stays onto I, J stays onto J, K stays onto K. So this is I3. So it's basically a diagonal matrix where you've got 1 on the diagonal and 0 elsewhere. So I guess the difference is that you've got many neutral element for matrix multiplication here, many ones. So I4 would be like that. Okay. And if you multiply, those are actually here different identity matrix, and they are square matrices. They have the same number of rows and column. Identity matrices. And a property of identity matrices, like I said, is that they keep things where they are. So if you do x I2 times x, well, you get x. If you do I3 times x, well, you get x again. Okay, of course here x would have x here would be, in this case here, it would be a vector of length 2. Here would be a vector of length 3. And also, if you do A times I, you perform a linear transform. You actually, well, A times I is what? You do I, you do a linear transformation with standard matrix take a look at this maybe first. I times x, it will give you x. Okay. So in some way, AI is the same as A for all x. For all x, because no matter what x is, that's essentially doing I first doesn't change anything. It keeps things where they are. So the IX is just x. So in fact, from this, we could actually deduce that or conclude that in general, if you do A times I, you're going to get A. Okay, so it doesn't change the product if you multiply by I. If you do I times A, you're going to get A again. Okay, maybe an example, if I have got the matrix 2, 3, 1, 1, 0, 5, and I multiply that by I. Now, what is going to be the size of I? Well, I will have to have 3 rows, right? So it's going to be 3 by 3. Otherwise, the multiplication wouldn't be defined, right? Because this is 2 by 3. So this one has to be 3 by 3 for this to work. You can check if you multiply by I, you're going to get back 2, 3, 1, 1, 0, 5. And if you take 2, 3, 1, 1, 0, 5 and you multiply that by I, but I would have to be now 2 by 2 because that's, remember, that's 2 by 3. So this would have to be 2 by 2. You're going to get back, you can check, 2, 3, 1, 1, 0, 5. It doesn't change the result of the product.